Hello, in this study we're going to look at computing factorials. So, a recursive method is one that invokes itself directly or indirectly. Many mathematical functions are defined using recursion. Let's begin with a simple example. The factorial of a number n can be recursively defined as follows. 0 factorial equals 1, n factorial equals n times n minus 1 factorial, which is n greater than 0. So, how do you find n factorial for a given n? To find 1 factorial is easy because you know that 0 is 1 and 1 factorial is 1 times 0 factorial. Assuming that you know n minus 1 factorial, you can obtain n factorial immediately by using n by n minus 1 factorial. Thus, the problem of computing n factorial is reduced to computing n minus 1 factorial. When computing n minus 1 factorial, you can apply the same idea recursively until n is reduced to 0. So, let factorial n be the method for computing n factorial. If you call the method with n equals 0, it immediately returns the result. The method knows how to solve the simplest case, which is referred to as the base case. The base case is where recursion stops, or the stopping condition, same as the base case. If you call the method with n greater than 0, it reduces the problem into a subproblem for computing the factorial with n minus 1. The subproblem is essentially the same as the original problem, but it is simpler or smaller because the subproblem has the same property as the original problem. We can call the method with a different argument, which is referred to as a recursive call. The recursive algorithm for computing factorial n can be simply described as follows. If n equals 0, return 1. Otherwise, return n times factorial n minus 1. A recursive call can result in many more recursive calls because the method keeps on dividing a subproblem into new subproblems. For a recursive method to terminate, the problem must eventually be reduced to a stopping case, at which point the method returns a result to its caller. The caller then performs a computation and returns the result to its own caller. This process continues until the result is passed back to the original caller. The original problem can now be solved by multiplying n by the result of factorial n minus 1. So we can go ahead and reset the code animation. We can restart the animation here. So the program starts the execution from the main method, and the main method is pushed onto the stack. So here we'll enter a non-negative integer. So it's set to 3. Okay. Now we'll click next. So the program invokes factorial n. Factorial 3 is invoked and pushed to the stack. The value of n in the main method is passed to the factorial. And the statement tests if n equals 0. It is false since n is 3. The program invokes factorial 3 minus 1. Factorial 2 is pushed to the stack. The statement tests if n equals 0. It is false since n equals 2. And here we have that the program invokes factorial 2 minus 1. Statement test if n equals 0, and it's false because it's 1. Factorial 0 is invoked. And the statement returns 1. Factorial 0 returns 1 and is removed from the stack. Factorial 1 is on top of the stack. The statement returns 1 times 1 from factorial 1. Factorial returns 1 and is removed from the stack, and factorial 2 returns top of the stack. The statement returns 2 times 1 from factorial 2. Factorial 2 returns 2 and is removed from the stack. Factorial 3 is on top of the stack. The statement returns 3 times 2 from factorial 3. The statement displays the result. The method is finished and is removed from the stack. And that's how the animation works. So now we can look at it actually applying this. Right? We have our library that we're importing. We're creating our public class. We have our main method, and then we have the factorial method. So the method that we want to update here is the factorial method, and the thing that we're going to check is n equals 0. So if n equals 0, and we'll check that. And the code's correct. So the factorial method in lines 16 through 21 is essentially a direct translation of the recursive mathematical definition for factorial in the Java code. The call to factorial is recursive because it calls itself. The parameter passed to factorial is decremented until it reaches a base case of 0. So now we've seen how to write a recursive method. Now we can look at how recursion works behind the scenes. So figure 18.2 illustrates the execution of recursive calls starting with n equals 4. So we can start the animation here. Return 4 times factorial 3. Return 3 times factorial 2. Return 2 times factorial 1. Return 1 times factorial 0. And then finally return 1. And then pop these off the stack. Okay, now we're seeing the recursion being undone. This is the unwinding phase of recursion. So finally, factorial 4 is evaluated. So we go through and we actually do the calculation. Returns 1, returns 1 times 1, returns 2 times 1, returns 3 times 2, returns 4 times 6, which is 24. There we go. So let's go through a couple of exercises here to challenge yourself. Stop the video here. Read these questions. And ask yourself what the answer is. So, okay. Now let's check the answers. So what is a recursive method? What is infinite recursion? A recursive method is one that calls itself. An infinite recursion is one that never stops. How many times is the factorial method in live example 18.1 invoked for factorial 6? Stop the video here. Okay, let's look at the answer. 7 times. Invoking factorial 6 involves invoking factorial 5, 4, 3, 2, 1, 0. This is a total of 7 times of invoking factorial 6. Show the output of the following programs and identify the base cases of recursive calls. Here we have A, which has a method called xMethod. An xMethod is takes an integer value, and if that value is equal to 1, return 1. Otherwise, return xMethod with n minus 1. We have another example, xMethod 1, 2, 3, 4, 5, 6. And we're going to call xMethod on that. So we want to get the output of the following programs and identify the base cases of recursive calls. So for the first one, the sum is 15 times 5 plus 4 plus 3 plus 2 plus 1 plus 15. And then the other one is 97,654,321. So, write a recursive mathematical definition for computing 2 to the n for a positive integer n. Stop the video here. Okay. The answer is fn equals 2 if fn equals 1. Fn equals 2 times 2 raised to the n minus 1 for n greater than 1. Okay. Write a recursive mathematical definition for computing x to the n for a positive integer n in a real number x. Stop the video here. So, fn equals x if n equals 1. Fn equals x times x raised to n minus 1 for n greater than 1. Let's write a recursive mathematical definition for computing 1 plus 2 plus 3 for positive integer. So fn equals 1 if fn equals 1, and fn equals n minus 1 plus n for n greater than 1. Okay. Which of the following statements are true? Every recursive method must have a base case or a stopping condition. Right. Every recursive method calls the original problem, bringing it increasingly closer to a base case until it becomes that case. Infinite recursion can occur if recursion does not reduce the problem in a manner that allows it to eventually converge to the base case. Every recursive method must have a return value. A recursive method is invoked differently from a non-recursive method. So, that answer is correct.